Hi, in this part of the tutorial we'll take a look at eavesdropping security for multiple messages and CPA security. So the main question that I want to start with is the one that we had the PRG-based encryption scheme, and that kind of worked okay, right? But it had the drawback that we can use keys only once. So in order to overcome this, in order to come up with an encryption scheme that where we can use the keys multiple times, we just came up with this PRF-based scheme, and then that happened to be CPA secure anyway. And for CPA security, we knew that we can encrypt multiple messages because, well, the adversary can ask for multiple encryptions. So if key reuse was a bad thing, then something bad should happen there in this experiment as well. However, it seems like we did too much of a step, right? We immediately went from eavesdropping security, where I could only use a key once, to CPA security. However, we also saw security definition in between those, which is the multiple message eavesdropping game that we have here. And in this definition, in order to be secure, also the scheme needs to be able to handle multiple encryptions with the same key. Why do you see this? Well, the adversary in this game submits two vectors of messages, and one of them is encrypted. But he then gets like a whole vector of ciphertexts and needs to decide which of the two message vectors were encrypted. So if we, for example, use the one-time pad in this multiple messages eavesdropping game, then this would just fail horribly, and any adversary would have an easy time of distinguishing the two message vectors if he chooses them like kind of cleverly. And then we went ahead and defined chosen plaintext indistinguishability, CPA. And we also noticed that it's equivalent to multiple message indistinguishability with CPA. And in these games, let's take the upper one, A is allowed to ask for multiple encryptions on plaintexts of his choice. Okay, so there this multiple, using the key multiple times comes from these queries. And then eventually he sees one ciphertext for a message M0 or M1, needs to guess which one. And now my question is, if the multiple message eavesdropping game already covers the fact that we can use keys multiple times, why even come up with CPA security? Okay, maybe take a second and think about it yourself, whether you can answer this. What's the actual difference between those two games? You may have spotted the difference. It is that in the multiple message eavesdropping game, the adversary needs to fix all of the messages at the beginning. So he sends all of the messages that may be encrypted, and then he gets all of the ciphertexts at once. Here, in the CPA game, those plaintext or those messages that need to be encrypted, the adversary can choose adaptively, meaning that he can ask for encryption of P1, see the ciphertext, and then decide, okay, which plaintext do I want to see an encryption of next. And this actually sounds like a small difference, I guess, but it makes a world of difference in cryptography in general. It's also a more realistic model, if just in reality, right? Because if I were able to make someone encrypt certain messages, then I'm probably going to be able to do it also after seeing some of the ciphertext that they already sent. So now my question is, can we kind of formalize this? Can we come up with a way of showing that this security notion of CPA security is actually strictly stronger than the security notion of multiple message eavesdropping? And how would we show something like this? Well, we would show that there exists an encryption scheme which is multiple message eavesdropping secure, but it's not CPA secure. And then we know that like CPA security actually seems to be a stronger thing. You can take a little bit of time to think about it. I have one hint as to what direction you can think about, which is those weak messages that we've seen before. We've seen that there are certain kinds of weak messages that just rule out chosen plaintext indistinguishability, they will probably also rule out multiple message eavesdropping security. And we've seen a way of introducing weak messages that is just not exploitable at all. So it's still CPA secure if you do this. But maybe there's a little bit of a middle ground that we can use to construct a scheme that can be broken by a CPA attacker, but cannot be broken by an eavesdropper. And I have one more hint for you, if you haven't solved it yet. Think about how to maybe hide a weak message so that the CPA attacker can actually find it, but the multi-message eavesdropping attacker has no chance of finding it, or will only find it if it's already too late. Okay, so let's do this. We'll start by, we start with a CPA secure encryption scheme, and then we weaken it so that it becomes possible for a CPA attacker to attack it, but still isn't possible for an eavesdropping attacker to, or for multiple message eavesdropping attacker even, to attack that. And then we change the encryption algorithm so that we introduce two things. We introduce this weak message, which I call m star. And the thing will be that this weak message, I choose this randomly from the message space, which let's say it's just 0 to the n. And then I store this in the key. When I say that's a weak message, then I mean it like in the sense that we had in the previous video, where we introduced weak messages, and a weak message is one where encrypt will always just use the 0 randomness to encrypt it. And then kind of the idea is that as soon as you find the weak message, you have broken the whole scheme, because then you can cleverly choose your messages and break the whole thing, as we've discussed before. Now that we have this weak message, right now nobody can find it at all. It's a random message, so the CPA attacker cannot find it, and the multiple message eavesdropping attacker can also not find it. What we want to do now is we want to enable the CPA attacker to actually find out what m star is, so that the CPA attacker can break the scheme while the eavesdropping attacker cannot. We do this as follows. We say that encryption, if m is equal to 0, then we output the proper encryption of 0, but we append the weak message to it. It's still an encryption scheme. We need to change the decryption such that it ignores this, this m star in the decryption part. But that's easily done. Now what have we gained? Take a second and play through how you would attack the scheme as a CPA attacker, and why you can't do this as a multi-message eavesdropping attacker. Right, so as a CPA attacker, I can basically just query for p1 equal to 0 to the n. Then I would get the weak message m star. And then I can choose my challenge to be m0 to be m star, choose m1 to be whatever, get the ciphertext, then ask for an encryption of m star again, and if the ciphertext matched, then I know that it was m0, otherwise I know it's m1, as before. However, as a multi-message eavesdropping attacker, well, I don't have any chance. I can query for, no, I can't query. I can use m0 here as one of my messages, but I need to fix all of the other messages that I'm sending there already in this moment without knowing the ciphertext that would give me this m star. So as a multi-message eavesdropping adversary, I would indeed learn m star, but I only learn it as soon as I get the ciphertext here, and at that point it's too late. I can't ask for more encryptions, I can't retroactively change my pick or something. It just, it's too late. So essentially the only weakness that we introduced into the scheme, which is this weak message here, it cannot be exploited by the multi-message eavesdropping adversary. You can make this more formal and do an analysis of of the probability that an adversary can actually break the scheme, but not break the original scheme. And the other case distinction would be whether or not he can find the message. And that's already it. We have found an encryption scheme, albeit a somewhat artificial one, that is secure in the sense of multiple message eavesdropping, but it's not secure in the CPA sense, which shows us that CPA seems to be the much better model because less schemes are secure actually under this. So ideally, we would always use a CPA scheme. Thanks for watching.